Okay, so these are notes. If you guys want to just sit back and relax, jot a few things down. It's entirely up to you. This covers a lot of the things that we talked briefly about in the handout yesterday. We're talking work, kinetic energy, and potential energy. And here we see a cartoon version of Mike who's doing some, what is that called? Olympic lift? Is that the clean and press? Okay, so is he doing work? On the barbell? Yeah, because he's applying a force and the barbell is moving, right? And the force is in the same direction as that it's moving.
We didn't do any sound problems.
We're going to do those at the end today. So in the everyday sense, work involves pushing, pulling, lifting, that kind of stuff, right? Work is the measure of the amount of energy that is transferred when a certain force acts through a certain distance to do some job. So there must be transfer of energy by way of a force through a certain distance to do some job. And the force has to be in the same direction as the displacement. So, horizontal force applied to a dynamics cart for a certain distance. Work is done, energy is transferred to the cart. The cart now has kinetic energy. When I push the cart and give it kinetic energy, I'm doing work. It has more kinetic energy at the end. I've done work. Okay, what about work, energy transfer, and potential energy? Lifting an object like bricks or a cardboard box or something like that, right? And we talked briefly about this yesterday as well. When objects are lifted, work is done. A certain force is exerted through a certain distance. Energy is used up or transferred to get the job done. When I lift a book in the air, I give it potential energy. I transfer energy. The vector cereal that I had this morning. Anybody have vector this morning? Look and see how many kilojoules in a bowl of vector cereal.
So once you stop moving the book, though, it's not working?
There's no more work being done once you're holding it there, right? Because there's no distance. Well, yeah, I still have to do the... the kinetic energy of the bricks is zero, right? When you lift it up, there's no more kinetic energy. Where did this energy go? It's been transferred into what we call potential energy, stored inside the bricks. Can you see potential energy? Like, is it, if you pull it apart? It's just there, right? It's kind of a hard concept to sort of define. Everybody kind of gets it, but it's hard to define. Right? Potential energy is energy that is stored in an object because of its condition or position. When I say condition, what kind of examples are we talking about there? Like if well, that would be position, right? We're talking about condition. We're talking about like elastics that are stretched or springs that are compressed, right? That kind of thing. Something that's bent is going to flex back. Energy is stored in an object because of its condition or position. Position, of course, would be a big boulder on top of a mountain. Here's the other example. When we stretch out or push in a spring, we do work on it, transfer energy to it. We say this work goes towards increasing the potential energy of the spring. And there are formulas for springs. There's a lab that we do called Hooke's Law Lab. I think it was Robert Hooke was his name that devised that little experiment. In general, anytime work is done, energy is transferred to an object and increases either its kinetic or potential energy. It could also be an increase in chemical potential energy, right? It doesn't actually say gravitational, but potential could be chemical, gravitational, or even electrical, right? When you charge up your phone, you are taking electrical energy from the wall and you're storing it in the phone's battery, right? Potential energy. Yeah, okay. Good to know. Okay, there's no big surprise here. Work is proportional to the applied force. Work is proportional to the distance moved. Work is not related to time. Whether you do a job fast or slow makes no difference. It still takes the same amount of energy because it's the same job. Whether I lift the book fast or lift the book slow, it still has to have the same potential energy at the top. So work is not related to time. Work is proportional to FD. Hold the fort here. I thought work was equal to FD. Well, every time you change a proportionality statement to an equation, you have to insert a k, a constant of proportion, right? And sometimes that constant is things like pi. In uniform circular motion, our constant was 4 pi squared. But in this case, because we're defining what work is, like does work exist except in mankind's mind?
What?
Does work exist? Like, I mean, is it something that you can measure, or is it something that we've kind of invented? It's kind of invented, right? And so, especially the units, right? If F is measured in newtons and D is meters, what we can do is name it after a guy named Joule. There he is. Obviously, he didn't do a lot of work shading.
6 minutes.
6 minutes. Wow. Feeling the love. I think I should give everybody a scorecard.
That was actually pretty good, though. When you think about
Yeah?
It involved work, and we're talking about how work is fictional.
You're thinking maybe 6 or more?
I think 6 is pretty good.
Oh, that's good. Feeling good about today. So yeah, I can't remember his first name, but it's Joule. Last name Joule. So what we did was we just said 1 joule is 1 Newton meter. In other words, we set the K value equal to 1. 1 joule is the amount of work done when a force of 1 Newton acts to a distance of 1 meter. In other words, the K value is simply, go away. No, it's not there. I guess I have to write it. I don't know. Work equals FD. In other words, the K is simply set to 1. Because we get to define the unit, we as in humans, we're just going to say, yeah, the K value is 1.
Oh, is that what the K on my calculator is for?
No.
Like sets on the K.
No, I think that's something else. That's a different concept. Can you see? I've seen that
Put
before.
it in, so then like.
Okay, so nothing too exciting there. We've kind of covered that yesterday. So I just sort of covered the same thing 2 different ways. Let's go straight to those sample questions from yesterday. You guys all did them, right? Yeah. Sample work questions, right?
How would we? I didn't know how to do this. I don't think.
Okay, so sample problem. This is the same question, is it not? Work done against friction. How much work is done when sliding a 30 kilogram chair at a distance of 15 meters across a rough surface where the force of friction is 50 newtons? Oh. Okay, so you're pushing the chair, but friction is pushing back with 50 newtons. Now, it doesn't say it, but it doesn't say there's an acceleration, so you have to assume that it's at a constant velocity, which means the acceleration is 0, which means that your applied force must be equal to your friction force of 50 newtons. In other words, the 30 kilogram chair doesn't make any difference at all. The applied force is equal to the friction force.
How do we figure acceleration 0 again?
It doesn't say that there's an acceleration, so you're going to just have to make that assumption, right?
I just find out the force.
The force of friction is 50 newtons. If the acceleration is 0, it's not doesn't have a net force, which means that the applied force over here, whatever I'm pushing with, has to equal the friction force of 50 newtons. And it's a distance of 15 meters, so it's just 50 times 15, which is 5 times 15 is 30, 60, 75, 750 newtons. How did I do that multiplication in my head? I don't know, I'm just asking.
10 times 5 and 5 times 5.
You could do it that way, yeah. I went 5 times 15 is 2 times 15, which is 30, and another 2 times 30 is another 30, plus another 15 is 30 plus 30 plus 15 is 75, and then add a 0.
Yeah, 10 times 50 is 500, and 5 times 50 is
You
250.
could do it that way too. All good.
2 steps, bigger numbers.
Yeah. So what about work done against gravity? How much work is done in lifting 2 bricks, each of mass 1.4 kilograms, from the floor to the top of your table, which is a distance of 80 centimeters? So we're lifting 2 bricks. Does it matter if I do them one at a time or together?
Yes, no.
Nope. The 2 bricks will have the same gravitational potential energy at the end. What is the force required? Well, I'm working against gravity, so it's going to be 2 times 1.4 times 9.8. God, I'm going to need a calculator for. Correct answer. 27.44 newtons, right?
Okay. Force.
Yeah, but that's not the end.
No, that's not the end. The work done now is FD 27.44. The distance is 0.8. 21.95, and that's measured in joules of work. You're a bunch of. A 1.5 kilogram dynamics cart is pulled at an angle of 30 degrees above the horizontal with a force of 25 newtons. The cart moves 4 meters. How much work is done on the cart?
Lots.
No, you can't just say lots. 30 degrees, right? The distance is 4 meters. First step is to do what? Find the horizontal component, right? So FH is going to be F cos theta, or
So the main,
25 cos 30,
the main like formula here.
W
is,
equals FD.
Yeah.
I get 3.86. Oh, that's in radians. That's no good. Seems right. 5 times 30 cos. 21.7. So 21.7 newtons of force is actually put into it going sideways. W equals FD. 21.7, the distance is 4 meters. 86.6 joules. So, amount of work to pull the cart up the planes. If you're, that's not what I wanted to do. If I'm going to pull it up the plane, I need an FA. There is a force down the plane. Remember, FD is the component of gravity that acts down the plane. Okay, so FG is equal to mg sine theta. So we've got a 30 kilogram box. Gravity is 9.8. The sine of 30. I'm what? Oh yeah, well it's Throwback Thursday, right? I get 147 newtons of gravity pulling down the plane. Because it's, because that is the same as, it's this triangle here. No. It's like this, right? Yeah, this is theta here. This is F perpendicular, right? This is weight force, and this is FD, and so it's, yeah. So now the amount of work done is W equals FD, so now it's F times D, it's not F small d, right? So it's 147. Now, how long is the ramp? It looks like it's 6 meters. 3344 joules of work.
There's.
Amount of work done lifting the cart straight up. What if I just wanted to lift it from ground level up 3 meters? Well, then it would be,
A lot more work.
would it be?
So it'd be same amount of work. Something else.
The FW is going to be 30 times 9.8, 294. W equals FD, 294 times 3, and what do you get? The same number.
No.
Why are these the same?
Same amount of work.
Same amount of work. Why? When the box is sitting up here, it's gonna have the same gravitational potential energy whether you pushed it up the ramp or you lifted it straight up. The advantage to going up the ramp is that you use less force,
More time.
but you have to use longer time, longer distance. Now, the problem with ramps is that there's gonna be friction. So if there's 50 newtons of friction force, well then your applied force is gonna be FD plus the friction force, so it's going to be 147 plus 50, 197, W equals FD, 197 times 6 meters, $11.82. So even though it's easier to go up the ramp, you still have to do slightly more work. Where does the extra work go? Where does the extra energy go?
That's on
Heat. Heat. No, it has the same potential energy at the top whether it was pushed or lifted there.